Thank you. And all right, let's start. For the next, wait, Wednesday is a holiday, isn't it?
Tuesday.
Tuesday.
It's a holiday.
Or Tuesday or is it Thursday? Yeah.
Tuesday.
I think it's Tuesday. Okay, so today we're going to be talking about statistical models and how to estimate probability distributions of data. Specifically, we'll be looking at maximum likelihood estimation and expectation maximization. This lecture is in two parts. Today I get through all the boring math. Next week I get through all the boring remaining details, right? So here's the basic problem. You want to estimate the distribution of some data. For example, the roll of a die. What is the distribution of the outcomes of a die? What do we call it? Pardon me? Uniform, no. So is it a multinomial distribution? I've lied on the slide, right? I do it every year and try to catch if anybody knows the actual name of the distribution of the outcomes of a die.
Bernoulli.
Okay, you're getting close. How many outcomes can a Bernoulli trial have? 2. Okay. So if a trial can have multiple outcomes, what's it called? That's not binomial. Binomial is just, counts of 2. What's the difference between a Bernoulli and a binomial? Can you say that aloud, please? So a Bernoulli trial is the outcome of a single toss of a coin. A binomial is the number of heads in n tosses, right? These are 2 different distributions. A multinomial is the number of outcomes in n rolls of a many-sided die. The basic distribution itself is actually called a category distribution. I had this on the slide. For some reason, it's not showing up, right? So every time I speak of multinomial distributions, you really should be thinking of category distributions, but we will be using the multinomial property of it to estimate the category distribution. That's why I'm going to be calling it the multinomial. So a dice roller rolls a die, and you plot the histogram of outcomes, right? So what are the parameters of the of this distribution?
Number of sides.
Number of sides. Yeah. The probability of each side, right? So now, based on the outcomes of these dice, we want to estimate it. So you have an estimation problem. Or you might have something like this, where you have battery just out. I think I have a spare batteries. Give us a second, please. Thank you. So here's another experiment. You draw a bunch of outcomes from a distribution. In this case, I'm assuming it's a Gaussian distribution. So the left shows the histogram of a collection of such observations. In fact, this histogram came from real data. These were Kepster coefficients from a collection of speech. And the histogram has a specific shape. So now if I want to know the distribution of this data, I'm going to have to assume some nature for the distribution, some form. And here I could assume, based on my knowledge of the shapes of various distributions, that it's Gaussian. The parameters of the Gaussian are the mean and the variance. So the problem would be that of estimating the parameters. Now, in each of these cases, we have a problem of estimating a probability distribution from observations. And the assumption, of course, is that there's an actual natural probability distribution for the data. You may or may not know it. It may or may not have the specific formulaic form that you decide on, but you're going to assign something to it and you're going to estimate its parameters, okay? So here's the agenda of what we're going to be talking about in the next couple of lectures. We're talking about generative models, fitting models to data, and trying to obtain closed form solutions for these fitting, which you often will not get, and how you can deal with missing information and expectation maximization. That's how we can solve all of these and the world's problems and, world hunger and all of that with EM, okay? So the first thing, what is a generative model? A generative model is a model for the probability distribution of a data, like a multinomial, or more specifically, a category distribution, or a Gaussian, right? And there's a computational equivalent for it. We're calling it a generative model. So there's the assumption that there's a process which generates data. Now, in real life, if you consider any particular variable, like the heights of people, it has a distribution, right? So there's a real distribution, which you're never going to know. What does it mean to say that it has a real distribution? It turns out that this is a very abstract question. It's much harder than you would imagine, right? And so we're going to work off assumptions and hypotheses. So our hypothesis is that there's this magic box, and every time you kick it, it's going to output a value. And so this box is activated with a random seed. The outcome is a value. And if you plot the histogram or plot the distribution of all of these values that it would generate on repeated excitations, then that histogram is going to look like the distribution that of the data that you actually have in real life. And so the computational equivalent of estimating a distribution is a generative model, a model that can be used to generate data with a distribution similar to the given data X. And of course, anytime you think of something like this, then it's not so simple, right? You have to worry about where did that seed come from. We're not going to make any claims about the seed at this point, just the nature of the generative model itself. But once you begin thinking about it in these terms, then you have to worry about where did the seed come from? The seed came from another process, and that had another seed, and where did that come from? And that came from another process, and so on, right? Anyway, going back, here are some simple generative models. The first one is your standard category distribution, or your multinomial probability mass function. This is for discrete data. So your outcome V belongs to a discrete set, like the rolls of a die. So the rolls of a die can have 6 possible values, right? So here, the parameters of the distribution are the probabilities of the individual outcomes. This holds when the number of possible outcomes is finite and countable. Now, you can have other discrete distributions where the outcomes can be infinite, but they're still discrete, like the number of times the event happens in real life. It can go up to infinity. In that case, you obviously cannot be enumerating the probability for every possible value of this outcome. You're going to need a formula like the one over there, which is a Poisson distribution, which is the probability of lambda raised to k e raised to minus lambda over k factorial is the probability that any specific outcome takes the value k. For continuous valued functions, you have probability distributions like the Gaussian. Now, everybody's familiar with the Gaussian, right? It's the exponent of a quadratic. And it has a nice bell shape. And once again, in every case, so the parameters are the mean and the variance. These are all generative models. These are models for the distribution of data, right? And so when I'm trying to characterize the distribution of a data, I'm going to assign a generative model to it. I'm going to try to learn the parameters of this model. And then as far as I'm concerned, that is the true distribution of the data. Whether that's really the case or not is not something that we'll dwell on. So how do we estimate a generative model for data? So let's say I'm given some set of observations, X. I'm going to choose a model, P of X semicolon theta, where theta represents the set of parameters of the model itself. And you want to estimate the theta such that P of X semicolon theta, this is the functional form, right? Which varies with X. Best fits the distribution of the data X that you just saw. So The idea is that if I've got a collection of data and make my distribution a best fit to it, then it's also going to generalize to other data from the same source. So here's an example, multinomials, so more specifically category distributions. The dice roller rolls dice, and you plot the histogram of outcomes. So the histogram of outcomes is shown to the left with the colored bars. And the parameters to learn are P1 through P6. I'm giving you two choices, the ones shown to the right. Which of these two do you think is the one that represents the distribution for the dice? The first or the second? Second, why? There's a match, right? Here's another example. The figure to the left shows the histogram of a collection of observations. Again, these were the Capstell coefficients from speech. And I'm going to model it with a Gaussian. The parameters of the Gaussian are the mean and the variance. I'm giving you a choice of 3 different Gaussians on the right. Which of these do you think was the true distribution of this data? The red one, again, why? There's a perfect match, right? In doing these, in giving me this notion of a perfect match, that you based your guess on things matching what you saw. So there was an implicit assumption in all of this. What was this assumption? Yes. That the observations must be likely under the model. There's something even more extreme than that. You're right. Right? So we are assuming that the data, that the distribution is characteristic of the data. But there's a much stronger assumption over here. And the assumption is that the world is a very boring place. So the whole concept of maximum likelihood estimation or statistical estimation is the world is a boring place. In fact, it's so boring, so boring, so boring that whatever you have observed is extremely typical of the world. And so the maximum likelihood principle can alternately be stated as the world is boring principle, right? In this case, whatever you saw was extremely typical of the process that generates the data. And so now, given a collection, a set of possible options, you're going to be choosing the option for which these data are most typical. That makes sense, right? So that's the principle over here. So you want to select the distribution, and how do you quantify this? You want to select the data that has the highest probability of having generated these data. That's what you mean by being typical, right? Of all the possibilities, you want to choose the one model for which these data are most typical, most probable, right? And so using the world as a boring place principle, you want to choose the one distribution which has the highest probability of having generated these data. And so if I use that principle to our to the 2 examples that we just saw, right? For example, if I have a 6-sided die, then I roll it a bunch of times, and then I get the outcome 1 n1 times, the outcome 2 n2 times, 3, 4, and 5, 5 and 6 occur n3 and 4 and 5 and 6 and n6 times. What is the probability of getting this particular set of outcomes for a 6-sided die?
Since we assume that they're independent, we can multiply the probabilities for each of them.
Right. So absolutely right, or almost completely right. There was an extra term. What is that?
Like some segments choose multinomial choose n1.
Correct. So all the ways in which you have a total number of outcomes, which is n1 plus n2 plus n3 to n6, right? All the ways in which you can partition it to n1 instances of one category, n2 instances of two categories, the second category, and so on. That's a combinatorial term. And so the probability of getting this particular set of outcomes is going to be that combinatorial term times the probability of 1 occurring n1 times, which is p1 raised to n1, times the probability of 2 occurring n2 times, which is p2 raised to n2, and so on, right? So this here is the probability of this particular set of outcomes. And if I take the logarithm of it, then And why do I take the logarithm? Because I don't like this term. It's got a lot of multiplications. I prefer additions in real life because they are easier to deal with when I'm performing any kind of calculus. So that simply becomes the log of the constant plus the sum over all possible outcomes of ni times log of pi. Ni is the number of times that outcome happened, and pi is the probability of the outcome, right? And similarly, if I had a collection of Gaussian observations, right? Now, anyway, so when I'm trying to estimate the probability distribution for the dice, I want to estimate the parameters P1 through P6 such that this thing is as high as possible. That's the world as a boring case principle, right? I'm going to pick the one dice for which this set of outcomes was most probable, the dice that was most capable of generating this particular set of outcomes. And so I want to maximize this probability on top, but because the logarithm is monotonic, I can maximize the log probability instead. And this, of course, I know how to maximize this. There's one. How would I maximize this? Anybody?
Sure.
Mm-hmm. Can you speak up, please? If I take the derivative and set it to 0, will that solve the problem for me? Or is there something missing? There must be a constraint. The probability is sum to 1, right? And how would you include that? I can just use a Lagrangian term out here. And then when I take the derivative and equate it to 0, I'm just going to find that my best guess for the probability of the ith outcome is ni divided by the total number of outcomes, which is what you were always told, right? That if I roll a dice n times and I get the number 1 n1 times, then the probability of 1, my best guess is n1 over n, right? Where did that come from? That is just your standard maximum likelihood estimate. So same thing. If I've got a collection of observations drawn from a Gaussian distribution, then the total probability of all of these observations, assuming they're all independent, is the product over all observations of the probability of the individual observations themselves under the Gaussian distribution, right? And so in this case, the log probability is simply going to be the sum. Again, I want to find the Gaussian parameters that maximize this. Alternately, I can find the Gaussian parameters that maximize the logarithm of this one, right? And so that's going to give me the log probability, which is some funky formula. It's a quadratic. And I can maximize this with respect to the covariance matrix theta of the Gaussian. I can also maximize this with respect to the mean mu. Without going into the math, if I work it out, you get this familiar formula. The mean of the Gaussian is simply the average of the data, right? Now, anytime I asked you what the mean of a collection of data was, this is exactly what you would have given me. This was just counting, right? But it turns out that that is, in fact, the maximum likelihood estimate for the mean of a Gaussian distribution, assuming the data was drawn from a Gaussian distribution. So also, the formula for the covariance over here, this is something that you guys are familiar with, right? It's the average of x minus mean times x minus mean transport, basically the outer product of centered vectors. And this was the formula that you always learned in school. This was what the probability distribution for the variance of a data set was. It turns out that that's just the maximum likelihood estimate for the variance of a Gaussian. So again, things that you're familiar with, it just descends to counting, right? Now, here's another distribution. This is a Laplacian distribution where the probability of any outcome falls off exponentially as the distance from the peak increases. Now, there are two parameters to this distribution. One is the position of the peak itself. The second is how fast it falls off. So the Laplacian distribution is given by 1 over 2b e raised to minus of x minus mu over b, the magnitude. So x minus mu tells you how far you are from the peak. Mu is the peak. And the b controls the rate at which it falls off, right? Once again, if I got a collection of observations, so b is a scale parameter. Once again, if I got a collection of observations from this data, from this distribution, then the log probability of the collection of observations is simply going to be the sum over all observations of the log of this term, right? So you get a constant for there's n log b minus the sum over all observations of the distance of x from the mode divided by b, right? And if I differentiate this with respect to the individual terms and equate it to 0, I'm going to get an estimate for b and mu. So mu in this case, it turns out, is going to be the median of all of your data. If you've got a collection of data, you find the point where, what on earth happened? You find the point where half the data lie on one side, the other half lie on the other side. And that's your best guess for mu. And b is simply going to be the average rate at which x falls off from as it goes away from mu, right? So all of these formulae, there's nothing magical about these formulae. These are things that you just look at the probability distribution or look at the data, and you'd come up with these formula based on counting strategies like the mean, the variance, the median. As it turns out, in each and every case, these are just maximum likelihood estimates of the parameters of the distribution, assuming the specific model that you've got. And they're all based on this very common principle that whatever you have observed is very typical of the process, that the world is very boring, right? So far, so good. Any questions? I haven't spent a lot of time on this because I'm assuming that all of this is obvious to you. Questions, you guys? Questions?
There's a question.
Yes.
Difference between a multinomial and category.
So a category distribution is the, hang on. So P1 through P6, this is a category distribution. If I roll a dice, then the probability of getting 1 or 2 or 3 or 4 or 5 or 6, there are only 6 possible outcomes. That's a category distribution. Whereas a multinomial is, I roll the dice n times. What is the probability that I'm going to get n1 of 1, n2 of 2, n3 of 3, and 6 of 6? So the probability of getting this particular set of outcomes, that's a multinomial distribution. The probability of getting any individual outcome is a category distribution. One is an extended version of the other. It's the difference between a binomial and a Bernoulli variable, right? Okay. Any other questions, guys? Any other questions? Yes, no. Okay. And so you have other more complicated distributions. Now, in all of these cases, right, the answer was obvious. The mean is the average. The mode for the Laplacian has got to be the median, right? The scaling factor, how far it falls off, you can literally just take the average of how quickly the values fall off as they go away from the mode. So in these cases, the answers were very obvious, the maximum likelihood estimates. And you didn't have to think about it in terms of the maximum likelihood principle. They just sort of popped out, often seemingly out of intuition. You can have more ugly distributions like the Dirichlet distribution, which is defined on a probability simplex. It has a very ugly formula, which I won't go into. But the point is that if I have a collection of observations from a distribution of this kind, and I want to estimate the parameters of the distribution, I'm actually going to have to work through the arithmetic, where I write out the formula for the probability distribution, and then I'm going to have to solve it. And a situation like this is one where you don't get a closed form solution for it. You'd actually have to run an optimization algorithm to find the parameters of this distribution. So in fact, the majority of probability distributions have this property, that even though the maximum likelihood principle itself is very simple, applying it to estimate the parameters of the distribution is going to be devilishly hard. So we often just work with the simplest models because those are easy to deal with. But the reality is that real life is a lot more complex. That should have been 2023, 1102. My slides, yeah. I updated the slides, but for some reason it's not showing up, right? So it's MLSP 23, 1102, 123. It's just MLSP 23-1102 without the 2022, right? -1. Okay. Anyone want to answer the first one? False. Second, true, right? Easy enough. That the true model is not always the most likely model, right? It might just be a random outcome. It's just a guess. That's just a principle that we work with. It won't necessarily hold in every case. But it is true that in many cases that this just descends to simple counting-like solutions. Okay. Any questions so far? This was the easy bit. Then it gets a little more complex, right? So now I'm going to complicate the problem a little bit. The guy is no longer simply rolling a single dice. Somehow, for some crazy reason, he dug into his pocket, he found both a dice and a coin. And so now he flips the coin before he rolls the dice. And if the coin turns up heads, he calls out the number on the dice. But if the coin tells a tail, he calls out the number of the dice plus 1. All you get to hear are the outcomes, the numbers that he calls out. How do you estimate the probability of heads on the coin and the distribution of the dice?
Addition.
Pardon me? Yeah, but how do I get the distribution of the dice?
Distribution.
Right? So, or let me give you something even a little more ugly. So this guy has 2 dice in his pocket, right? He rolls them both. He always calls out the sum. Based on just the sum, how do you estimate the distribution of the individual dice? Yes.
We are assuming like regular, evenly weighted 6-sided dice. Right?
No, these are loaded dice. Otherwise, it's 1/6 for each of those, right?
It's cheating.
Yeah.
Are they the same kind of dice or did
It doesn't matter, right? They're 6-sided dice.
don't think we can work it. I feel like we do need some information, but maybe we don't.
How would you do it?
Model the sum of,
Pardon me?
we model the sum of any.
I can model the sum, but what are the probability distributions of the individual dice?
You want
So assume the dice to be the same, each of the dice to be
I'm not assuming that they're the same. They can become very different dice.
the similar kind of model for each of the die and assume they are independent.
Okay.
You want model the sum.
If I model the sum, I'm getting the probability distribution of the sum. Am I getting the distributions for the individual dice?
The sum in terms of the distribution.
So what is that going to look like? Yeah.
U1, U2, U3.
So, and I can make this even a little more complicated, right? I have 2 of these guys rolling dice in a room. And there's a fellow standing at the door. He's the one calling out the numbers. There's a red guy and a blue guy. And the red guy is rolling a red dice. The blue guy is rolling the blue dice. And this at each turn, this guy randomly selects one of the 2. And then he calls out that person's number. Based on just the collection of numbers that he calls out, how do you decide the probability distribution of the individual dice? Now, as I keep going down this line, this begins to look more and more, challenging to say the least, right? And so here, or even worse, I've got a bunch of guys sitting with Gaussian distributions inside the room. And then I have the crazy man at the door. At each turn, he just picks one of the random Gaussians and draws a number from it. And he just calls out these numbers. And then based on this collection of numbers, how do you know the probability distributions, the parameters of the individual Gaussians? From? Good perform. That's a really bad answer. We know that you can't mix Gaussians and separate them using ICA, right? Gaussians are the one case where they won't work. So Yeah, in each of these problems, there was some information missing. And if this information were available, you would be able to compute the answer, right? In the first question, if I knew if it was a head or a tail in each row, in each trial, then it's easy enough for me to give you both the probability of heads for the coin and the probability distribution for the dice. But that information was missing, right? In the second case, if I knew the outcome for any one dice at each time, then I know the individual outcomes for each of the dice. And now I have two collections. And from those two collections, I can compute the probability distribution for each of the dice, right? Or in these two cases, if I just knew which dice shooter the guy selected, or which Gaussian the fellow selected, then I have the numbers that came out from each of these individual dice, for each of the individual Gaussians. And from those, I could compute the probability distribution of the individual dice or the individual Gaussians, right? The problem is that information is missing. And so we have a situation where we're dealing with missing information. And this missing information makes things ugly, right? So these are just some examples of missing information. You can have missing information in different forms. So I'm going to show you two different ways in which information can be missing. One in which you might have information missing about the underlying data itself. The other in which you might have information missing about the underlying process. So questions, anybody? Zoom, any questions? No? Okay. So let's look at information missing about the underlying data, right? Here's a problem. We just already saw a problem where I gave you a collection of vectors and I asked you to estimate the Gaussian distribution for it, right? And if I have a collection of vectors of this kind, it's easy enough for me to compute the Gaussian distribution. I just estimate the mean, which is the average. I estimate the outer products, the average of the centered outer product that gives me the covariance matrix. All is fine. And what was the principle we used to come up with those estimates? That was the maximum likelihood estimate, right? Easy enough. But then I have this modified problem where I have all of these vectors, but in each vector, several of the components are missing. The blacked out components are missing, right? And so if my vectors are now incomplete, how would I estimate the probability distribution of the Gaussian, the parameters of the Gaussian? Yes.
Like mean difference of each component, and anytime you need to like estimate one of the missing components, you just use it.
That's one way of doing it. How about the covariances, for instance, right?
So you would just have the variance of each individual component, and anytime you have to estimate like that value.
But what about the cross covariances, x1, x2, right? You're going to, as you begin looking at more and more things, you find more and more stuff missing to compute your estimates, right? Now, this is not a hypothetical problem. Anytime you went on Netflix in the past or any of these recommendation engines, this was basically what you had. Yeah, Hari? So you just said you can just perform the estimations component by component. But then that's not going to be the full answer because you want the cross correlations. And why is that important? So for example, if you went on Netflix and you saw some movies, right? Or whatever the latest movie recommender engine is, it's going to recommend other things to you. How did it know which ones to recommend? You'll find it surprisingly accurate most times, right? So every person, there's a collection of 1 million movies that they have. And so this is the set of ratings given to 1 million movies by one person. But the average person has not watched 1 million movies. The average person has watched a few dozen movies at the best, right? In the best case. So the most of the numbers are missing. And so now we have this collection of vectors in which many components are missing. And based on this collection of incomplete vectors, you have to estimate a probability distribution and the covariance between the different terms so that the next time somebody watches a movie and gives it a rating, you can go through the covariances and say you're more likely to, you're likely to appreciate these movies, right? So it's a known problem. But then how do you actually compute a covariance matrix of this kind? So now the original problem, going back to our maximum likelihood problem, we wanted to estimate the Gaussian given a collection of data vectors, but we know how to do this given complete data vectors, right? So, and a complete data vector X, if each of these was considered called a vector X, the data set, the uppercase X represents the complete set of vectors. And we are going to try to estimate the mean and variance such that the log likelihood of the complete data is maximized, which is the sum over all vectors of the log of the probability of the complete vector, except that we have the situation where we only have incomplete vectors, right? These are all the data that you have observed. The remaining components have not been observed, right? So if I'm applying the maximum likelihood principle, do I apply the maximum likelihood principle to this data, assuming that all components have been observed, or this data, which only tells me the components that have been observed? Which one would I apply the ML to? The second one. You can only make assumptions about what you have observed, right? You want to say that whatever I have observed is the most typical thing in the world. And so these are the actual data, comprising only the observed components of the vectors. And we are missing all of these components, right? And the complete data includes both the missing components and the observed components. And again, keep in mind that the complete data are not available. The missing components are missing, right? And so maximum likelihood estimation is only going to maximize the likelihood of the observed data, the green components. The black components have not been observed. There's no question of maximizing the likelihood of something that you do not know. You can only maximize the likelihood of things that you have observed, right? Unfortunately, the Gaussian is defined on the complete vector. It's not defined on the incomplete vector. And so if I want to compute the probability of the complete vector in whatever I have observed, I must compute it from the probability of the complete vector, right? And each vector has observed components and missing components. And so the probability of the complete vector is the joint probability of the observed and missing components. And to obtain the probability of just the observed components, I have to marginalize out the missing components, right? By integrating those things out. And so when I actually compute my maximum likelihood estimate, I can only compute the log likelihood of the data that I have observed, which means that I must be computing the sum. What I really want to compute is summation over O log of P of O. This is all I can compute, but to obtain P of O, I have to marginalize out the missing components. And this must be done vector by vector because the components that are missing are different for each vector, right? And so this is what we're going to have to maximize. And so our maximum likelihood estimation ends up being this ugly formula, which is maximize with respect to mean and sigma the sum over all vectors of the log of an integral of a distribution over all the missing components. And so now you have the log of an integral, right? This is not going to be something that you can optimize. It's not going to happen, right? It doesn't have a closed form. What is the log of an integral? What is its derivative? And how do you maximize it? There's no closed form in almost any case. And so here you have a problem, right? So we looked at an issue of information missing in the form of incomplete data. That was one case. The second one is when you have missing information about the underlying process. So here, this would be like the guys in the room, right? Two guys rolling dice and someone calling out the numbers, or mixtures of Gaussians, right? So here, we have these two guys. Consider the dice problem. We have these two guys rolling dice, and the dice are loaded differently for each of them. You have a fellow at the door who's calling out the probabilities, randomly selecting one of the two dice and calling out the outcomes, right? How do you determine the probability distribution of both of the dice? And the way to think about it is that this fellow, at each trial, he randomly selects one of these two dice, right? So there's a two-step process. In the first step, the fellow selects the dice. In the second step, a number is drawn from the dice. So the probability of generating any particular outcome is, if he's got the red dice, the probability that he's going to call the number 6 is the probability that he chooses the red dice, and the probability that the red dice rolls a 6, plus the probability that he chooses the blue dice, times the probability that the blue dice rolls a 6. That's what it's going to be, correct? So in general, the probability of getting any particular observation is the sum over all of the individual components of the probability of choosing that component and the probability that that particular component generates the given observation. And our objective here is to learn the probability distribution of both the dice and also the probability with which he calls the individual dice. The individual multinomials are selected. And again, note the process actually draws two variables, right? So in any given draw, so here's the key piece. In any given draw, there were two variables chosen. The first variable was which? It was fast. That was meant to wake all of you up. Come on. I need a better clicker, right? So in any given draw over here, there were two variables chosen. First is the individual multinomial component itself, and the second is the outcome that came from that component. So a single draw actually selected two variables, the K and the O. You just happen to observe only the O. And so if you want to get the total probability of getting a particular outcome, choosing the red dice and the red dice generating the number 6, it's P of K times P of O given K. This is the probability of choosing the red dice. This is the probability of the outcome given from that dice. And the overall probability, as we just saw, is the sum over all components of choosing that component times the probability that that component is going to generate the given observation. And of course, in the ideal case, if you had the complete data is the entire sequence of variables that was invoked in any given draw. So the complete data over here is going to include which multinomial rolled the dice and what the outcome was. It's going to be K and O. And if I had the complete data, then it's easy, right? I had the red dice, I had the blue dice. So every number that came out colored. And then all I would have to do is to segregate the two sets of numbers out. And then from the blue set, I can give you the probability distribution for the blue dice. From the red set, I can give you the distribution for the red dice. And then by counting how many blue balls and how many other red balls I have, I can tell you what is the probability of selecting the blue dice and what is the probability of selecting the red dice. Just straight up counting, right? Our problem is that the color is not given. So our data are incomplete, which means we don't have any way of segregating the data out, right? What we really want is the combination of O and K. What we are getting is just O alone. And so if I want to go back and look at the maximum likelihood procedure, the only thing that I've observed is O. So I want log of P of O. That's all I can compute. This is what I must maximize. But then P of O over here is, and I must maximize log of P of O with respect to both the probability distributions for the individual multinomial components and the distribution with which I'm selecting the components, right? And the probability of an individual outcome, I'm calling it a vector, it should just be any outcome, right? Is going to be P of a K times PKO, right? So when I stick this formula in to my maximum likelihood estimator, once again, I end up with a logarithm, with a summation inside the logarithm. And so I'm trying to maximize this term over here. I'm trying to maximize this with respect to both PKO and P of K, except that what I'm maximizing is the log of a sum. And you can't just differentiate it and equate it to 0. Because if I differentiate it, the first thing that happens is that those terms end up in the denominator, right? You can't just equate it to 0. So you won't get a closed form solution for it. So this includes the log of a sum, which defies direct optimization. And so here's the problem, right? So we saw the case for shooting dice, but for more general distributions like the Gaussians, you still have the same problem. You have a bunch of Gaussians, and for any given outcome, the process first selects the Gaussian, then it draws the number or the vector from the Gaussian. And so, although the overall distribution of the outcomes that come out can look pretty complicated, like so, right? It's actually observations drawn from a bunch of different Gaussians. So it's a Gaussian mixture. And the probability of getting any particular outcome O is the sum over all Gaussians of choosing the Gaussian, the product of sum over all Gaussians of the product of the probability of choosing the Gaussian times the probability that that particular Gaussian could generate the given observation O, which is simply a standard Gaussian distribution with the mean and variance for that Gaussian, right? And now our objective is to estimate these means and P of K given just a collection of observations O. Once again, observe that the process actually draws two variables in each draw. First, it chooses a Gaussian, then it draws an observation from the Gaussian, right? And so the probability of any particular draw must follow the entire process to the end, choosing the Gaussian and drawing the observation from the Gaussian. So for each outcome, if you had all the information about how the particular observation was generated, you would know which Gaussian was drawn and the observation. So you're going to have K comma O, right? And the probability of that particular sequence is the probability of choosing the Gaussian and the probability of that Gaussian generating the number O, the observation that you just did. And of course, the probability for any individual outcome is simply the sum of P of K comma over all Gaussians. And again, if I look at this in terms of the complete data, in the ideal case, with respect to every data vector O that you saw, you would know which Gaussian it came from. So if I color my Gaussians red, blue, green in my example, right? Along with each data vector, you would have the color of the Gaussian that it came from. And so in order to estimate the parameters of the Gaussian, all I have to do is to segregate all of the data out. These came from the blue Gaussian, these came from the red Gaussian, these came from the green Gaussian. And once I segregate these things out, I can compute the means and variances for the individual Gaussians quite trivially using my standard formula. I can also compute based on the counts of vectors that came out from each of the Gaussians, I can compute the probability of selecting any individual Gaussian. That too works out. Everything just works out. Our problem, of course, is the color of the Gaussians missing, right? We don't know which Gaussian each vector was drawn from. So we have no way of segregating the data. Our data are incomplete. We want a combination of the data and the identity of the Gaussian it came from. Instead, we only have the observation O. And so when I try to perform my maximum likelihood estimation, I'm maximizing the log likelihood of the data that I did observe. But then P of O, we know is the sum over all Gaussians of the probability of the Gaussian and times the probability of the observation from that Gaussian. So if I stick this formula in to my maximum likelihood estimator, once again, I have a log of a sum, which is going to be very ugly for me to optimize, right? So in all of these cases, we have a general form of a problem. Regardless of whether I was looking at the data where the data components were missing, or whether I was looking for data where the process outcomes were missing, steps in the process of generating the data were missing, right? The result is the same. I have missing data or missing variables. And had these things been available, estimation would have been trivial, but they are not available, so I have to marginalize them out. And in the process of marginalizing them out, I end up with an estimation of this kind where if I represent all of these missing variables by the symbol H, then for each observation, the log likelihood, the log probability of what I did observe is the log of the sum or the integral over H of the joint probability of H and O, where H is the data that you didn't actually get to see, but you would have liked to see, right? And the sum of and the log of a sum or an integral makes direct optimization of these formulae really challenging. Right? No closed form, you need iterative algorithms. Questions? This was the easy bit, then I throw math at you. So this is your last chance to ask questions before you get confused. Assuming that you are no. So again, MLSP 23-1102-2. Okay, Alex, first statement true? Second one, is the second statement true? Third, fourth, right? So MLE with missing data does not yield problems with closed solutions. There are no closed form solutions because if there were no sum inside the log, wait, I don't even know what that second statement means, right? But you're right. So here's a problem that we've got. We have a problem where you have the log of a sum, right? And the summation is occurring because I'm trying to marginalize out H, okay? Now, I cannot solve this problem. So because I have the log of a sum and this makes the optimization challenging. Can I replace this with an approximation that's more tractable, which will still give me the solution? It may not be a closed form solution immediately. It may give me an iterative solution, but can I change this with approximate this with something that's more tractable? That's our approach to the problem. So here's what I can do. We have log of summation over H, P of H, comma O. This could be an integral. I'm just going to use the term use the summation, right? So I can multiply and divide by some function of H, Q of H. Q of H is the property that it's always non-negative, and it sums to 1 over H. Basically, Q of H is also a probability distribution, right? So if I write it this way, is this term different from this one? No, it's the same, right? So I can write it this way, log of summation over H, Q of H times PH, comma O divided by Q of H. Everybody with me? And it turns out that when I write it this way, I can pull the Q out, and this becomes a lower bound. So that's because we have this property, which is that the logarithm is a concave function. So the log of x, this is x, this is log of x, it's going to look like this, right? So if I take any value x1, and if I any other value x2, any point in between can be written as alpha x1 plus 1 minus alpha x2, where alpha lies between 0 and 1, right? It's a convex combination of the two. If alpha is 0, I'm just going to get x2. If alpha is 1, I'm just going to get x1. Now, if I compute the value of the function here and the value of the function here, so let me call this, say, x prime equals alpha x1 plus 1 minus alpha x2. So write this here is f of x prime, right? This is the logarithm of x prime. But if I draw a line between these two, over here. Any point on the line is a convex combination of these two values, right? And specifically, this point is going to be alpha of f of x1 plus 1 minus alpha of f of x2, because it's directly on the line, right? And it's a fraction alpha from the initial point. That makes sense to everybody, right? And so what we get, yeah. Was there a question?
We can't see the board.
Okay. Fortunately, I have the picture on. Right. I should have a picture here. That solution explains it, right? So, can you see the board now? Okay, so which portion? Can you see any portion of the board?
Well,
Yes, do you,
This side.
do you see the board to the left?
yeah.
Okay,
And
fine.
then-
I can use the board to the left. No worries. So here's what I have. If I have log of x looks like this, right? And if I have x1 and x2, then any point between these two, let me call this x prime, is going to be of the form x prime equals alpha x1 plus 1 minus alpha x2, where alpha lies between 0 and 1. So this guy here is going to be log of alpha x1 plus 1 minus alpha x2, right? And on the other hand, so this one is log of x1. This one here is log of x2. And if I draw this line between the two, this point here is going to be the convex combination of log of x1 and log of x2, which is alpha times log of x1 plus 1 minus alpha times log of x2. And what you can see from the curve is that the convex combination of the log is always below the log of the convex combination, right? So alpha log x1 plus 1 minus alpha log x2 is going to be less than or equal to log of alpha x1 plus 1 minus alpha x2, because log of x prime here is out here, whereas this is the convex combination of the logs of x1 and x2. I can generalize this. That's just for 2 points. But if I have a collection of points, it's very easy to extend this and show that if I have a bunch of values x1, x2, x3 through xk, then the log of a convex combination of these x's is always going to be lesser than the convex combination, or greater than the convex combination of the log of x's. And so going back over here, this is the log of a convex combination of p over q. And this is going to be greater than or equal to the convex combination of log of p over q, right? So log of q times p over q, log of the summation over h of q times p over ph over qh is going to be greater than or equal to the summation over h of qh times log of ph over qh. That's basically just restating what we have in this picture. And that's all we need to know, right? So once I know this, I can generally say that the term to the left, which is simply the log of the probability of the observation, it's log of P of O, right? That is going to be lower bounded by summation over H of Q of H times log of PO, O comma H divided by QH. So long as the Q's are all non-negative and sum to 1, right? Any questions about this? Zoom, any questions, any doubts? There's nothing particularly fancy that I've said, right? So the term to the right is called a variational lower bound on P of O. It's always going to be lower than P of O. It doesn't matter what the nature of P is. It doesn't matter what the nature of Q is. So long as Q is non-negative and greater than and sums to 1, this must always hold, right? And so this is what we're going to take advantage of. I can say that log of P of O with parameter theta is always going to be lower bounded by the average taken with respect to Q of log of P over Q, right? And I'm explicitly showing you the parameter theta in both cases to show the dependence that these are models, right? And so the model have a parameter theta. It's called the variational lower bound, also sometimes called the empirical lower bound on P of log of P of O. Now, how do I use this? This is what it means. Now look at this guy over here. This term to the left is a function of theta, right? Because if I vary my parameter theta, that log likelihood is going to change. The term to the right is also a function of theta. If I vary the parameter theta, that's going to change. So if I plot both of these as functions of theta, the red curve may be my log likelihood of the observation itself, log of P of O semicolon theta. The blue curve is going to be the term to the left, which is the variational lower bound. So the term to the right, which is the variational lower bound with also as a function of theta. And what this little formula tells us is that the term to the right, regardless of how you choose Q, is always going to be below the log likelihood of the data itself. So far, so good, right? Now, you have come up with a lower bound, but then I can come up with a tight lower bound. What is a tight lower bound? I can choose my Q of H such that the gap between the red and the blue curves is as small as possible. And with an appropriate choice of Q of H, I'm going to get a lower bound of this kind. And the assumption that is that if I get a sufficiently tight lower bound, if I maximize the lower bound, it's going to be pretty close to the maximum of log of P of O itself. Again, everybody with me so far? Okay. So to make the lower bound tight, we want to choose Q of H properly. And now, so what is a Q of H that will make the lower bound tight? We actually end up defining a function of, again, two variables. Let's say I have, where's my eraser? So there's a bit of ugly math over here, but hopefully the pictures will make it clearer, right? Oh, shoot. I can't write here. So, no, it's okay. Let me try writing here, right? So I want to come up with a Q of H, and I have P of H comma O semicolon theta, right? Now, this is a joint probability of H and O, but I can also come up with a conditional probability of H. I know, right? So P of H given O semicolon theta is simply going to be P of H comma O divided by summation over H P of H comma O. I'm not showing the semicolon theta. This is a simple enough formula, right? I can obtain it directly from the formula itself. No big deal. And so let's say, and these guys can be chosen at any particular value theta, right? So let's assume for now that my Q is a conditional probability of H given O at some value theta prime. Now this is a given value. Remember, I need a specified function Q. Q cannot be an open-ended function. It cannot be, a function of theta. I haven't really solved anything. So I'm going to make Q specific to some theta prime, okay? So if I write it like so, then I'm going to get log of O, P of O, is lower bounded by P of H given O at theta prime. This is summation over H, P of H given O at theta prime times log of P of O comma H at theta divided by P of H given O at theta prime. There's only one term which depends on theta over here, which is in the P of O comma H. The rest are theta prime. It's something that's given, right? So this guy here, this function to the right now has two thetas in it. One is a theta, the other is a theta prime, right? And theta prime is what we've chosen for our Q function. So let me just write it as J of theta comma theta prime. So then this J of theta comma theta prime is this term to the right, which is log of P of H given O at theta prime times log of P of O divided by P of H given O at theta and theta prime, right? So now observe this. There are two, this term, log of P of O is always lower bounded by j theta theta prime, regardless of what theta prime is. The second thing is that if I set theta to be exactly equal to theta prime, you simply end up with log of P of O again on the right-hand side. How does that happen? Like so. I mean, how did this happen? Why is j theta theta equal to log of P of O? Here's what it is, right? J theta theta, I've written summation over H, P of H given O times log of P H comma O divided by P of H given O. What is P of H comma O divided by P of H given O? That's just going to be P of O, base rule, right? Because P of H comma O is P of H given O times P of O. So this guy within the log simply becomes log of P of O. This is not a function of P of H. I can pull it out of the summation. So all that remains inside the summation is summation over H, log of P of H given O. I'm summing a probability distribution over the all values of the variable. The summation simply becomes a 1, right? And so as a result, this simply becomes log of P of O. And so using all of these, we end up with this crazy looking formula solution, which looks kind of mystical. You know, what on earth does all of this mean? We'll look at some pictures, and maybe the pictures will enlighten us, okay? But first, let's look at what this is. We have defined our j theta theta prime, which we will call our auxiliary function, which is a function of two different settings of our parameter theta. And it's the expectation over the conditional distribution of H given O when the parameter value is theta prime of log of P of H comma O divided by P of H given over theta prime, right? And we have the fact that the actual log likelihood is lower bounded by this guy. And when theta and theta prime are identical, this is actually the log likelihood that you're interested in. And so just using these two, you end up with a very cute estimation approach, where this is an iterative estimator, where I can start off with an initial value of theta. So this is fixed. This is my initial value. And then I maximize this with respect to, so this would be my theta 0, say. And I maximize this with respect to theta to get me theta 1. Then I plug this back in here and maximize this with respect to theta to get theta 2. How does this work? Do these equations give you any intuition? If it does, raise your hand. If I see any hands raised, I'm going to say you're lying. Right? It doesn't. But if you look at the pictures, it's very cute. Here's my picture again. The upper one is my log likelihood of O as a function of theta, right? So now my function J has two parameters, theta and theta prime, right? And what it means is that by choosing my theta prime over here, where on earth was that? So when I say that J theta prime is going to be log of P of O theta prime, it means that I can actually, the function J has two settings. It has two parameters. This is the variable, this is the parameter for J, right? So if I set the parameter for J as theta prime, say theta 0, then my auxiliary function is going to be touching my log likelihood at theta 0, because J theta 0 is the same as P of O log P of O at theta 0, right? But it's strictly a lower bound. And so the function J is going to have a function shape of this kind, and it touches the log likelihood function at the initial estimate, theta 0. Now I can maximize this guy. The second one is an easy function to maximize. And once I've maximized it, I've found a value here. And because I'm maximizing it, I know that the J here is greater than the J here. I also know that the log P is even greater, right? So I know that by going from theta 0 to theta 1, my log likelihood has increased, right? So now I have my new value theta 1. I can reconstruct my, so that's P of O given theta 1, right? O at theta 1. I can reconstruct my auxiliary function so that it now touches my log likelihood at theta 1 by setting the parameter of J to be theta 1, right? And then this guy can be maximized. And that's going to give me something that's higher still, right? And I know that the log of P of O is even higher. So I've increased log of P of O at theta 1 as well. And then so that's P of O at theta 2, which is the maximum of J when the J's parameter itself was set at theta 1. It was made to touch the original log likelihood function at theta 1, right? And then I can compose my new J, which touches the log likelihood function at that point. And then I can maximize it. And I can keep repeating this till eventually I get to a point where, you know, the function that I get, the J function that I get, is maximum at the current parameter value itself, which means I can't go up any further. The process makes sense, right? So although when you just look at the equations, it kind of looks kind of mystical. When you actually look at how we are composing it, the visual logic behind it is impeccable. It's very clean. Yes.
Till the math, they understood like why the J function should be a tight lower bound of the log of P. But after the looking at the graph, like I feel like it need not be a tight lower bound if we just assume like something like an approximator of the function at the
Okay, here's what it means. The tight lower bound is the best thing you can do, right? Having it touch there is about as tight as it can get. If it doesn't touch it, if it's going to be if it's slightly below it, then there's always the likelihood. So with a tight lower bound, you actually get a guarantee. If you don't have a tight lower bound, then you're going to have funkier situations like, say, this. So I have a curve here, right? And if this is my initial estimate, theta 0, if I have a tight lower bound, it's going to be something like that, correct? But if it's not a tight lower bound, then it's not going to touch over here. If it doesn't touch, then I might get a curve something like this. At this point, it's a lower bound. It's a lower bound everywhere, right? But when I maximize it, I'm not really improving matters.
Like I'm talking about like let the J function touch the log of P of O at that point.
Yeah, that is a tight. That is the tight lower bound. It's the best you can do.
It doesn't matter whether it at other locations it's below the function or above the function.
No, you cannot. If I touch it, then what stops me from drawing a function of this kind? Right.
Like tangential function at that point.
Okay, so then what stops me from drawing a function of this kind? Right. The point is just being tangential. So by touching it, it becomes a tight lower bound. That's the point. If it's not touching it, it's not going to be a tight lower bound. The tightest lower bound is where it actually touches the function itself. That's a that is the definition over there, right? So long as you don't, if you don't want a tight lower bound, it means it's not touching it. Then you have other issues coming in. Yeah.
But if J function touches the log function at that maximum.
So that if the J function is a lower bound, right? So if the J functions, again, the J function, the second theta in the J function is the J's parameter, right? So if I have a function of this kind, this is my log of P of O. If my J function is touching it right here, then the J function is going to be looking like something like this. The J function cannot be higher. If you maximize the J function, you're going to be stuck at the same point because it's always a lower bound.
So in that case, we won't be able to optimize further.
It's at a peak. That is a local optimum.
But if the peak of J doesn't coincide with the peak of the log function, can that be a case?
If the peak of J does not coincide with the log function, then if this is your P at any other point, okay, you're saying that if the J doesn't actually allow you to optimize further, that could happen.
It can be worse, because the slope tangents show means the slope must be the same at a point.
That is true. So long as the slope of O is not going to be is not zero, you can't have that happen.
It's like in the local cinema.
No, because here It can get stuck at local minimum, but if this slope is non-zero, then it has to go up, right? Right. Thank you. So any questions? Yeah.
So I choose like a combination of the J1, J0, J1, 2, 3, 4. High.
It won't be a tight lower bound. The latest J is the tightest lower bound always, right? You could choose a convex combination, but it's not going to be a tight lower bound. Any other questions? Right. And so this is how the little optimization works. And this is your EM algorithm, right? You're going to iterate over K until log of P of O converges. And at each time, you're going to compose the J as J has two terms. Theta is the variable. The second theta is the parameter, right? So initially you set the parameter to be theta 0 and you maximize J. Then you get the new maximum and make that the parameter and keep repeating the process so that you actually get to a local optimum. And now observe that there's a log of P of H divided by P of H given O. But the denominator is not a function of theta, right? So if I actually expanded it out, it's going to be the sum over all observations. Where's my sword? Of the sum over all observations of the sum over all h's of log of P of H given O with the current estimate of theta times log of P of H comma O with the variable theta. And the second term, because the second term was in the denominator, right? This is not a function of theta at all. So I can ignore it, correct? And so because I can ignore the second term, this can be ignored for maximization. I end up with the simple estimate where I compute the P of H given O with the current estimate of theta. And then I find the new estimate as the expectation of the log of P of H, joint probability of H and O as a function of theta, using the conditional probability of H given O at the current estimate of theta. And if I keep repeating this, and if I iterate this process, I'm guaranteed to finally find a locally optimal value of theta. So this maximizes an empirical lower bound and guarantees at least non-decreasing log likelihood with iterations, giving you a local maximum log likelihood estimate for theta, right? So the expectation maximization algorithm in summary, you construct an empirical lower bound function, J theta 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 k, which we also call the auxiliary function. And you iteratively maximize this. You can ignore the second term. You can just keep maximizing this term with respect to theta. And then you take the maximum, plug it in as the parameter, right? So that's the EM algorithm. Right. One final poll. And then the thing is, we've been through the math. What on earth does this math mean? We're going to come back next week and we're going to try to demystify this a little bit. Okay, first question, true or false? Second one. Thank you, right? Great. And so that's so much math. But what does it really do? We'll hold you in suspense until next class. Thank you, everybody.